in this case are formed dynamically by interaction, but we need to recognize it. And this is done with the help of minimal spanning tree model. And that is a model has been developed by Aichelin long ago. And in this case, idea is that clusters are recognized by the method applicable for kind of asymptotic final state interaction in coordinate space, and look for a correlation of the particle in coordinate space. And two particles are bound if the distances in the cluster rest frame fulfill the conditions that the distance to the neighbor less than 4 Fermi. And in this case, you can find the chain of particles identified as the clusters. Particles are, a new particle is bound in the cluster if in bins with at least one particle of the cluster we find these correlations. And what we used now, it was beyond the standard MST algorithm. We use an extra condition. We look for negative binding energy for identified clusters, that we know that this cluster is kind of bound in this case. Actually, there is another algorithm, which is a simulating annealing clusterization algorithm. And this is coming back to the idea of Doro and Randrup from '93. And here you are looking for the combinations of nucleon which are providing you the minimal binding energy. And here it's explained in this cartoon. You choose randomly one nucleon out of some bunch of nucleons and end it randomly to another cluster and compute, in this case, the binding energy. And finally, you select the configuration with the minimal binding energy. And this has been realized using Metropolitan algorithm. And here, this SAC algorithm has been used in PHQMD simulation by the NAN group very successfully to apply to low energy physics and very effectively finds clusters. And I just show one example because SACA is very important for finding heavy clusters because their binding energy is a really important issue. And here it's already calculation from PHQMD for heavy cluster in spectator fragments in some scenes versus the experimental measurement. And here we have a data by Aladdin collaboration. And PHQMD shows a nice agreement with Aladdin data for very complex cluster observables. For example, the observable which characterize the largest cluster, it's so-called Z-bound. It's a variable defined in the following way, which showing you the number of proton bounds in the cluster versus the max. Or it's a different type of multiplicity versus the bound for different type of clusters, or very complicated observables, what we call rise and fall, which characterize of the bound versus multiplicity of Z from 3 to 30. And here you see that it's provided even for heavy cluster rather good agreement. However, now we have to say that in spite of this successful description of the clusters, we are coming to the conceptual problems. And this is related to the cluster substability in semi-classical models. And the issue is the following. That QMD is still semi-classical models, whereas cluster is a quantum object. And QMD cannot describe in a fully consistent way the quantum object, because simply QMD cannot project to the ground state in the correct way of this bound object and respect the minimal average kinetic energy of the nucleons which are bound in this cluster. In quantum object, they respect this minimal kinetic energy, whereas in semi-classical QMD for ground state not. And this leads to the fact that the nucleon might still be emitted from QMD cluster, while in the corresponding quantum system, this would be impossible if they are bound. And it actually means that the cluster, which has been found to be bound at some time t, they can be spontaneously dissolved or simply separate from each other at some time t plus delta t when we make the next photography. And here actually, I should stress how it works, is because MST is a cluster recognition algorithm. We can apply it anytime. And MST is not forming cluster, it's recognizing cluster. It's looking if in this moment of time, some bunch of nucleons are staying close together and have negative binding energy. In the next time, it's looking again and making many photography over time. And then you can look for the whole history of these collisions and expansion of your system and see if cluster found in time t1 survived up to time t2, t3, and so on. And what we found is that because of this semi-classical origin, we are losing some cluster found in some time. And however, it means that it's of course a bad thing. It means that multiplicity of cluster are time dependent. However, we should say that the form of the final rapidity distribution, PT distribution, and ratio of particle are not affected by that. But still, how we can compare with the data? So, and how we can stabilize QMD clusters. And here I should say they're still much better than if you would do mean field, but still we have this stability problem. And here we use actually different ways, which are the first idea which we used in this publication was related to take so-called equal physical time, which can be estimated in the following way, taken in the following way: t is equal to 0 times cosinus hyperbolical y, where t0 is the time selected as the best description of the cluster at mid-rapidity. And if you come to the next rapidity, the system needs still some time to come to this rapidity. And this you can estimate like a hyperbolic cosinus of rapidity. And this was our first idea. And recently we developed another, in my opinion, much more convincing approach, which we call stabilization procedure. And here the idea is the following: we start with the asymptotic states for cluster and free nucleons. And then we trace the history of collision back in time, because we record all of that. We call MST, as I said, in many different times, and then we reconstruct which cluster has been found in each time. And then what we do for each nucleons in MST, we track the freeze-out time at which the last collision occurred. Then we recombine nucleons into clusters with a negative binding energy only if time of cluster disintegration is larger than nucleon freeze-out time. And by this procedure, we recover most of lost cluster. And this is illustrated on the right plot, which is showing result of our stabilization procedure for different energy from low to RHIC energies. And here you see the dashed line shows you the number of clusters, let's say before stabilization, it's all found cluster. And if you apply the negative binding energy collisions, you already reduce the number of, let's say, so-called bound cluster. It would be this one. And after stabilization, you recover the lost clusters to the full green line. Okay, but now I want to show you a couple of results which we obtained with the equal physical time scenario 1. And let's start with cluster production, light cluster production as a deuteron, triton, and helium-3 at 11 GeV, which is relevant for beam energy scan experiment of star. And here we compare actually with the old AGS data, which are available at different rapidities. And that is actually very, very nice to have rapidity dependence for the cluster formation. And here we show our calculation for the two cases of T0 in order to demonstrate uncertainties in this case. And you see, we obtain a rather nice form which describe experimental data for this light cluster production. The right part shows PT distribution of deuteron at 11 GeV taken at different rapidity slices from this plot, actually for each experimental point, which is present integrated over PT data. Here you see some data again from E864 collaboration for different rapidity beams, and the lines, it's PHQMD calculation, and you see that the form of the spectra is nicely reproduced. Now, let's go to the PT distribution of more heavy cluster like Triton and helium-3, again presented for different rapidity slices. And here you see the dependence of the time. What you take as T0 is a bit stronger, indeed. But by the way, the form of the PT distribution is in line with experimental data, which is also, I should say, rather difficult to obtain in microscopic transport approach. It's not obviously coming. It's already for us was a very nice indication that our dynamics seems to work in the right direction. And here, let's go to high energy of 30 GeV, and on the left plot, we present the deuteron, and on the upper plot, a deuteron rapidity distribution and PT spectra, and helium-3 rapidity distribution and PT spectra in comparison with Na49 experimental data. And again, these data available in some rapidity range from -1.5 for helium-3 to 1.5 reflected data. And here we perform our calculations for equal physical time approach scenario 1, and we obtain the right trend for rapidity distribution and very, very nice description of PT spectra. Now, let me show you excitation function for the proton, antiproton, deuteron, and the ratio of deuteron to proton and ratio antideutron to antiproton. And of course, if you look to proton, antiproton, it doesn't depend on the time when you have it. But however, for deuteron, as I said, here we didn't perform this equal time approach because the data corresponds to mid-rapidity. So it's showing uncertainties in selection of time where we look at mid-rapidity for the deuteron. But the tendency is in line with the data. And in this plot, we show PT distribution from 7.7 GeV to 200 GeV square root of S in comparison to the star data. And Again, since it's mid-rapidity data, we show that taken at a different time, just to show uncertainties in our model. And you see that PT data are very much in line with experimental star data. And in this plot, we analyze also coalescence parameter B2 for the deuteron and helium-3. And in left plot, you see the result for deuteron at 11 GeV as a function of PT, and on the right plot for helium-3, and the upper plot showing the deuterons, B2 for deuterons for central gold-gold collisions as a function of square root of S. So, and well, I should say here again, we used for this calculation as an equal physical time approach for compute B2, but again, seems to be that PHQMD reproduce, at least qualitatively, even such complicated observable, which is a coalescence parameter B2, which is rather sensitive to the dynamic of clusters. And now let me come to hypernuclear production. And fortunately, recently, the experimental data from star collaboration appears, and I will come to that. But firstly, let us compare with all data from E64 collaboration, and in the left plot, we have the experimental data from this collaboration for two types of clusters, hypernuclei, and the color symbol represent PHQMD result, which again reproduce a tendency in spite of course, rather large uncertainties related to the time where we look at that. And on the right plot, we show PHSD prediction for light hypernuclei for upcoming data at 30 GeV. And of course, we are looking for the data which would clarify this, the quality of our calculation. I should say that here we use a rather simple assumption on nucleon hyperon potential, which was taken as 2/3 of the baryon nucleon potential. And the final for improvement, of course, and that's what we are planning to do in the future. And let me now come to the recent star experimental data of fantastic quality, which were presented rather recently. It's a data at square root of S3 GeV. And here we have a rapidity, we have a PT spectra at different rapidities for proton, deuteron, helium-3, triton, and helium-4. And we compare with the results of star collaboration, and here you see that PHQMD provides a rather good description of the star data. It gives us confidence to go also to compare with hypernuclei, and here we have again the latest star data for hyper triton lambda with the lambda PHQMD result, and also PT spectra calculated at different rapidities. And what we see is that at least the trend of the data we can reproduce, even the absolute value here is not in a rather perfect agreement. I would say. And the question is, of course, how the formation of cluster occurs with respect to the general dynamics. And in order to answer the question which we raised in the beginning of the talk, how these clusters in this plot, we present normalized distribution of the freeze-out time of the baryons, nucleons, and hyperons, which are finally observed at mid-rapidity less than 0.5. And I should say here, freeze-out time is defined by the last elastic or inelastic collision. After that, only potential interaction of baryons can occur. And the left plot present freeze-out time at low energy 1.5 GeV, and the right plot at 40 GeV collision energy. However, you see that freeze-out time of baryons shows a rather similar profile since expansion velocity of mid-rapidity fireball is roughly independent on the beam energy. And now we can answer the question, where are the clusters formed? For that, we present a snapshot taken at time 30, which is represented as the blue lines on this plot, and 70 is red lines on this plot, of the normalized distribution of the transverse distances of the nucleons to the center of the fireball for different clusters, A equal 1, 2, and 3. And A equal 1, it's of course free nucleon, it's not a cluster, but here we have some clusters, A equal 2 and A equal 3, which is represented here. And what one can see is that in this transverse distance profile of free nucleons clusters, that is rather different. And the clusters are mainly formed behind the front of the nucleons of expanding fireball. And that's the reason why ice is behind the fire. As you see here, there is a shift between free nucleons and the clusters. I'm sorry if something appeared here, should be removed. And that's why clusters survive. They are behind the front of the nucleons. And of course, pions are far away because we are looking at mid-rapidity. Pions are fast. They escape rather fast from the middle of fireball. And then you have a, let's say, wall of the nucleons, and behind there are clusters. And that's why they have a chance to survive. Well, also, we performed some study when we wanted to compare with the coalescence model. And here we collaborated with HIC group of Markus Bleicher and Jan Steinheimer, because they perform extended study on the cluster formation using coalescence model. And here we perform the comparison in this plot for lead-lead collision, 7% central at square root of S 8.8 GeV. And here we show PT distribution of the clusters. And the red line shows the HIC result with the potential, and dashed line HIC in cascade mode, and blue line, it's PHQMD with potential, and dashed light blue PHQMD with cascade mode. And here we apply exactly the same coalescence model. That was a key point. We have two different dynamical models with a different treatment of potential and interaction integral. It's absolutely different, but we apply the same coalescence procedure, the same coalescence model, like in HIC to PHQMD and HIC. What we obtained is that coalescence, and also we compared to MST result, and we found that coalescence and the MST give a very similar multiplicity and YPT distribution. And however, PHQMD and UQMD have a very different potential, and dynamics, as you see here, strongly depends on realization of potential. And here I should say in UQMD, it's a non-relativistic realization of the potential, and it has very strong repulsive potential. That's why its red line is shifted. However, in cascade mode, the results of two models are really identical for the cluster formation. And here, by comparing our PT spectra, we looked later for the comparison of transverse because here we again use the options with potential and not potential, but let's maybe concentrate on the following line. Here, for example, orange line represents UQMD result for free nucleons. And the red lines, it's UQMD results for the clusters. And you see that the red line is shifted to the low RT region. It means that the coalescence as well also as a MST procedure show that the deuterons remains in the transverse direction closer to the center of heavy ion collisions than free nucleons. And it means that deuterons are behind the fast nucleons or pi and Winn, which is far away already. And this is a result independence on the model. Very, very similar result we obtain also for PHQMD. So, and that's again helps to understand these ice in the fire puzzle solution, that the clusters are behind the front of the nucleons and pi and Winn is far away. So now let me come briefly to the second part of my talk, which is related to kinetic mechanism for the deuteron production. And here, what we understand on the kinetic mechanism. The issue is that light cluster and particular deuteron, they can be formed by hadronic interaction by the following 2-to-2 reaction or 3-to-2 reactions. And also, of course, they can perform, they can have an elastic interaction with the environment. And the main issue is that hadronic reactions for the deuteron pion and deuteron nucleon scattering seems to be very large according to experimental data. And here this plot showing actually experimental data in comparison with some parameterization and separation to elastic and inelastic path used in PHQMD. But let's just look on the experimental data, which is presented here as red symbols and here as black symbols. And you see in the peak cross-section is reaching 200 millibar. Of course, it's in a vacuum. But still, this cross-section is huge and cannot be neglected. And it means that the backward reactions, according to time reversal symmetry, expected to be also rather big. And that's why we think that these reactions should be important. And actually, it was a study by the SMASH IMPT groups when they investigate such type of catalyzer reactions with the pions and the nucleons and formation, their influence on the formation of deuterons and heavy ion collisions. And what has been found that in RHIC at LHC energies, due to the large abundance of the pions, deuterons are dominantly formed by pion catalysis reactions, whereas at cis energies, due to the large nucleon abundances, because we have a baryonic matter there, the deuterons formed by nucleon catalysis reactions. And here there are two studies from SMASH collaboration, which they use hydrodynamical model plus kinetic formation of the deuterons. with the two types of the realization of these 3-to-2 reactions. And the first study performed by Dima Linichenko, presented on many conferences, related to the reduction of this reaction simplification to two-step process by introduction of some fictional d-baryon resonance d prime, and then it's instead of 3-to-2 reactions, you simplified it to 2-to-1 and 2-to-2. And more recently in SMASH, they performed the calculation of 3-to-2 transition rate. And here it's actually some example from their results for 7.7 GeV square root of S energies. And they found that this kinetic mechanism is very important for understanding of cluster production. And I should definitely mention the work of IMPT group of Chimenko, when they also investigated in microscopic way such type of 3-to-2 reaction with a pi catalysis, but they use the impulse approximation when you consider like a pi scattering on a nucleon in the presence of one spectator nucleons. But what is also important, they discuss in this paper the importance to account for finite size of deuteron, which they introduced by this Wigner function. And they found that it leads to the suppression of deuteron production in proton-proton reaction, which demonstrated in this plot. And what we do in our PHQMD approach, we reconsider all of these approaches based on our realization and accounting for some novel effect, which in our opinion should be there, which I want briefly to discuss. But let me firstly to remind how this reaction can be treated. Because the reaction 2 to 3, 4, whatever can be treated naturally in the transport approach. However, for the backward reaction, it's already rather difficult and complicated issue. And here we present Boltzmann equation. In Boltzmann equation, this collision integral, which can account for all dissipative process and hadronic reaction. And this has been derived by Wolkenkassing in 2002 and even generalized for full of shell treatment. But here let's stay with on-shell formulation. And this formula shows you how collision integral has to be computed, or how, of course, if you consider N to M reactions, you have to integrate over all final state and initial state N-1, because you look for some particle under investigation. And here you have a transition amplitude, and here you have a gain and loss term. And the collision rate for hadron I in the number can be computed as a number of reactions in the covariant volume d for x, which is a product of dt and dv. And if we, how one can compute this covariant rate, if you have reactions 2 to 2, then this transition probability can be even simplified if it depends only on square root of s. This complicated integral can be simplified to such simple formula when you have a square root of s depending on s and some kinematical factor. And then this transition rate can be calculated using stochastic probabilities, what we call, and with the test particle ansatz for distribution function f. Then this collision integral can be numerically solved for test particles, and just by performing these calculations in cell of volume delta V, where the reaction rate at each time step are calculated by such expressions. And this stochastic treatment has been introduced long ago, GSI calculations, and then used in the bumps, and later in SMASH. And of course, it was used in this study in PhD and taken also for PHQMD recent study. And of course, 2-to-2 reactions is simple, but if you go to n larger than 2, then you cannot relate in a simple way your transition probability to the cross-section. Then you have to calculate a fully transition amplitude and use detailed balance for this reaction. And if you use assumptions that transition in amplitude depends on square root of S, you can, of course, simplify the 3-to-2 transition rate for test particle ansatz by the following expression, where you have this transition probability and some kinematical factor and the ratio of phase space. And of course, it's related to the cell volume where you perform your calculations. And here, what is important, it's either spin factor, also and spin factor, which is accounting for possible combinations. And okay, that's what we realize on the computer. And in order to verify our implementation for such type of 3-to-2 reactions for deuterons, we perform box calculation when you put your transport model in a box and look how the system equilibrates, and you can compute the rates. And actually, you can 2-to-2 and 2-to-3 reactions can be computed in a two-way using geometrical criteria with the Kodama prescription or the stochastic method of Casing, and they can be compared between each other, and they found to be in a very good agreement independent how you compute that. And 3-to-2 rate they realize by the covariant rate formalism by stochastic method. And this plot shows our numerical result, which is here it's a proton neutron, and here it's a deuteron. And here we compare that to the analytic solution, which can be done, let's say, analytically, and we find a very good agreement. And also I should mention, we wanted also to compare that with the SMASH result, and if we use their parameterization for cross-section and their isospin content of the reaction which they took into account, we found a very good agreement also with the SMASH calculation. However, we went further, and that is a novel aspect in PHQMD, that for this reaction of pion catalysis, we took into account all possible channels. In the SMASH, only this reaction are taken into account. However, there are many other possibilities, and they are very, very important to account for all isospin possibilities, because in heavy ion collision you have all of these zoo of particles, and this reaction also should be taken. And that's what Gabriele Coci implemented all of this reaction in PHQMD, and here he performed calculations in a box which shows a nice detailed balance for each of these reactions. And however, if you take into account all isospin possibilities, it's enhanced your deuteron production by 50%. And this is a red line. It was a PHQMD calculation, and this was a comparison to the SMASH result. And they're a little bit higher, but you take into account it's absolutely different code, different cross-section, and different dynamics. And this is a really great agreement. So, but however, if we take into account all possibilities, we are higher by 50%. But I should say that PT slope is not affected by that, only absolute value. However, if you go to low energy, for example, square root of 3 GeV, which is related to the latest star data, then the number of pions are not very large, and then this isospin effect is already not so important. But definitely it's important for RHIC and for star data and beam energy scan. But that is not all, because what we have to take into account it's a quantum nature of the deuteron. And in this case, what actually, how we can model that? It related to the fact of that in coordinate space, deuteron has a finite size. It's not a point-like particle. It has a size, it has a big radius, it's elongated object. And of course, if you want to produce deuterons in a medium, when you have a lot of particles around, maybe it's not so good idea that there are some pions in between of the proton neutron, which has a radius 1.2 Fermi, 1.8 Fermi, sorry, and if there are other particles in between. So this finite size effect in coordinate space definitely has to be taken into account. Moreover, the deuteron has a wave function in momentum space that's rather broad distribution in momentum space. And these momentum correlations are also very important because a proton and neutrons then can form deuteron only if they have a, let's say, some particular momentum correlation. If they are low if P momentum, internal momentum of relative momentum of proton neutron is not very large. And we realize the first assumption in correlation coordinate space by excluded volume conditions. We assume that deuteron cannot be formed at higher density region, whereas the other particles, hadron and parton, exist inside some so-called excluded volume, RD. And this radius is taken to be as a physical radius of average mean value physical radius of deuteron is 1.8 Fermi. And what the result of this excluded volume condition is a strong reduction of the deuteron formation. It's really a very, very visible effect. And also it's shifting and time delaying kind of this deuteron formation. So now this modeling of momentum correlation of proton and neutrons, that's actually very much in spirit of IMPT, what Qiming presented. And here you see the diagrams of impulse approximation, but what we use, that correlation of the final particle should follow the actual distribution of nucleons inside the deuteron, which we adopted from the wave function of deuteron in momentum space from Paris potential. And what we do for the candidate deuteron, we calculate the relative momentum P of the interacting proton-neutron pair in the deuteron rest frame. We calculate the probability of p-n pair to bind into the final deuteron with momentum P, which is computed with respect to square root of this deuteron function, and bound pairs are selected by projection to this deuteron wave function. And it also leads to the reduction, very similar as excluded volume, but there is no shift in time, that is orange line in comparison to red line, which was excluded volume. But thus, we have a two effect which we related to the modeling of the quantum nature of deuteron. And now, if we account for the both of them, it leads to the very strong suppression of kinetic mechanism for deuteron production. And here I am coming to the result, which shows you the total deuteron production by kinetic mechanism and MST. And they're distinguished by color in my plot, MST, with stabilization already here for identification of deuteron is presented as a green color. And for kinetic mechanism, we use a red color, and the blue line is the sum of all the both mechanism. Left part shows the result when we present only excluded volume for the deuteron. And the middle part when we take only momentum projection, and the right part when we have the both. And what you see So actually, what is very important that kinetic mechanism and MST, they have a rather different rapidity distribution. And if you apply the both, then you very strongly suppress actually kinetic deuteron production. And what turns out that in our approach, the deuterons are mainly produced by what we call potential mechanisms. They are just bound by potential interaction, which is represented by this green line. And the total sum of the both mechanisms are very much in line with an A49 data. Also, PT distribution, which is represented on low plot, is very good in line with this data. Also, we found there is only small differences in PT spectra between two mechanisms. And actually, it's again showing it's very important to have data not only at mid rapidity, but at also at a larger rapidity, because it's sensitive to the mechanism for the deuteron production and can shed a light how this cluster has been produced. I think I should speed up a little bit here. I just flash some results when we did the same predictions for different energies and compare with an A49 data. And we found again the trend that only if we apply this suppression by excluded volume and projection to wave function of deuteron for the kinetic mechanism, we obtain a good description of experimental data. And also we analyze with our both mechanisms, the latest data from STAR collaboration, and here it's PT spectra for different energies from 7.7 to 200 GeV. And you see the kinetic deuteron in our approach are rather suppressed, and the dominant mechanism related to the potential interaction of formation of deuteron by potential interaction. And that is my final plot with comparison. It's excitation function dn/dy of deuterons at mid rapidity. And here you see the red line, it's kinetic, and the green line, again, it's MST with stabilization, and that is the sum. And now it's very much in line with data. And what we also say, since we use the stabilization algorithm, now it doesn't depend on time anymore when we make our, let's say, snapshot to make photography, let's say, in which we take our potential deuterons. So, and again, what I should repeat, potential mechanism and dominance for deuteron production at all energies. And I'm coming for my summary. I presented you our novel PHQMD microscopic and body transport approach, which provides a cluster formation dynamically by potential interaction among nucleons, and which can be identified by some recognition algorithm. And in this talk, I'm mostly concentrated on MST algorithm for deuteron finding. Also, we have a kinetic mechanism for deuteron production. And however, by accounting the quantum properties of deuteron modeled by the finite size, excluded volume, effect in coordinate space, and projection of relative momentum of the interacting pairs of nucleon on the deuteron wave function in momentum space, leads to very strong suppression of the deuteron production, especially in target projectile region. And what we found, it's rather good agreement with experimental data at AGS and at RHIC energies. And coming back to the question of ice and the fire, we identify the dynamics of our cluster production, and our analysis shows they are produced shortly after elastic and elastic collisions, and they follow behind the front of expanding energetic hadrons, pions, and nucleons, and that's why ice is not in the same place as a fire, so cluster are survived. And also we found that coalescence and MST give rather similar result in PHQMD and the UQMD transport approaches. So it's kind of model independent result. And as an outlook, of course, it's a lot to things have to be done. And we have to go to LHC energies, but it's numerous computational efforts, and we are rather limited in the computational resources. And what we are working on, it's momentum-dependent potential, which would be important for cis energies, fair energies, and low Bess RHIC energies also. And we also want to improve on realistic description of hypernuclear potential, which is important for hypernuclear production. And maybe we think of kinetic formation of light cluster, but here, of course, cross-section are known. There are very little experimental data on this issue. And of course, we want to extend our study on collective observables. And the new experimental data are definitely very much needed. And especially data would be very nice to have data in different rapidity distribution, which I stressed a couple of times in my talk, because the mechanisms are different for cluster production, also at different rapidities, and it would help to understand the dynamic. And also would be very interesting to have a data on V1, V2, and I know that STAR collaboration is definitely working on this issue. I thank you very much for your attention and your patience. Thank you very much.
Thank you, Elena, for this very comprehensive presentation. Now is question time. So any question or comments, please raise your hand. I already see many questions in the chat window, but if you have question, please also raise your hand.
Let's see if I see the chat.
Maybe we can go to the first question from the chat window. Feng?
Yes.
Can you?
Hi, yeah, I'm here. So yeah, thank you very much for a very nice talk. Yeah, on the very beginning of the talk, you have shown that you have shown a very impressive comparison between your PHQMD calculation with like SMASH or the other calculations, and you mentioned that the major difference that you have included the correlation between the particles into consideration. And it shows that you have shown the rapidity spectra on maybe page 4, I think. So,
yeah, at the beginning, yes. Oh, sorry.
Yeah. Maybe on page 4. So it shows that, that this page, yeah. So your result shows larger rapidity spectra in the middle rapidity beams than the other methods. So it seems that the contribution from the correlation between particles first is always positive, and then it's more prominent in the middle rapidity beams than that in the large rapidity beams. So is that because that the fireball in the middle rapidity beams expand faster, and the size of the fireball in the middle rapidity beam is larger, so that the correlation is that important?
Well, let me comment probably about this plot. Here, what we did, it was a kind of model study. We took a different model like SMASH and UQMD in cascade mode. And here it was in this SMASH approach, there is no kinetic deuterons. It's just SMASH cascade and the UQMD cascade, okay? So, and we just run it and apply on the top the same cluster recognition algorithm. The idea was, this was some numerical package which calls PSMT, developed by Victor Kireyeu for experimental purpose. He took this MST and dressed in this root environment and so on. And we apply the same model for the same cluster finding model for all these approaches. And what we see, this plot demonstrates the following, that correlations are very important, and especially it's easy to destroy correlations at mid-rapidity where your matter really sensitive to the different interactions. In the target projectile rapidity, there the nucleons just follow a path in the spectator, let's say, region, and they stay more or less together. But even there, here, for it's, look, it's a deuteron and triton. For triton, you already see very bad dissolution of the clusters. We have this plot for heavy cluster, and then it's even worse, even in target projectile when nucleon following together. But at mid rapidity, where the most of the interaction occurs, it's really very sensitive to keep the correlations. And of course, if you don't have potential, like in cascade mode, there is no reason for nucleons to stay together. And in PHSD here, we use a simple mean field potential, and it also doesn't keep well correlations, let's say. But in PHQMD, we use, as I presented, this skin time of potential, which is also rather simple, but turns to be effective due to this dynamics related to calculation of two-body forces between all nucleons, all baryons around. This allows dynamically to keep correlations, at least in a better way than in mean field approach. That's this plot demonstrates.
Oh, yes, I see. So you mean that in the middle rapidity, you have more correlations, more interactions.
Yeah. Yes,
the correlations are more important.
Right.
Another, I'm just curious, why the contributions from the correlation is always positive. I mean, it's always add more particles, not destroy particles.
Of course, you also destroy particles, but you are looking for clusters. You are looking for correlations, right? So your goal is to find correlations. Yes, of course, they are also by potential interactions. They can go apart because the potential can be repulsive also, right? So of course, but you are looking for correlations.
Okay, I see. Thank you very much. Can I ask another maybe minor technical questions? So you mentioned that in your MST stabilization algorithm, in that algorithm, you pick up a freeze out time. You say it equals time that the last collision happens, right? Yeah, here the time at which the last collision occurred, and I mean, you know that if there are some potential effect, then the freeze out time should maybe later, right? So, do you have any comment on that?
Yes, it's actually, of course, it's a good point. Look, that is a stabilization procedure which we put on the top of kind of semi-classical approach to repair a little bit, to come back to the quantum nature of the cluster production. And this part we cannot take into account. What has been done in reality, it's like that. You make this photography during the full calculation, which is a time costly, I should say, and you record the history. Then you look at very large time, for example, 150 over C. You find the clusters and you find some free nucleons. You start to look for these free nucleons, why they are free. And if you find that at some time they were part of clusters, but then without any reason, without any collisions, let's say they kind of became unbound, what we call freeze out time, because they didn't have further interactions. It was no collisions. Then we bound them back to clusters. And of course, how to say, you can assume that their potential trajectory could go apart, but that is not the case, because we look for few time slices. If they were in a few time slices together, then at least probability that there is some big change in the potential is very low. Most likely it's due to this semi-classical dynamics. Simply, they just go apart and later you don't find them. But of course, fully exclude that we cannot. That's true.
Okay, thank you very much. I'm done.
Thank you. Now, since I didn't see anyone raise hand, let's go to next question in chat window. Kaija, could you ask directly?
Yes. Can you hear me?
Yes.
Oh yeah. Hi, Amina.
Hi.
This is Kaija. Yeah. Thank you.
Yeah, hello.
Very much for your nice talk and mentioning our work with Professor Tsuniko. So I have two questions. One is that so have you checked whether your method have the correct thermal limits in let's say in a box calculation? Because a dynamical model should have a correct dynamical model should have the correct thermal limits for light nuclei if you put a nucleon in a box, like what Dima has done in his kinetic paper.
Yes. Okay. Can I answer the first question? Yes, it's exactly. Sorry for being a little bit fast in the second part. That's of course, yes. It's related to kinetic deuteron. I think your question related to these reactions.
Not only a kinetic part, but also the potential part.
But potential part in thermalized matter has no meaning in some sense to look for clusters in this case, because you cannot do that in the box for potential deuterons, because you have you would have it's working for asymptotic state when you cluster going apart from the medium, and in the medium everything in equilibrium. Potential in this case has you have a homogeneous environment, so it doesn't work. It doesn't work. But for kinetic deuterons, here we definitely did it as it was the first check, and that is one of the example. In upcoming paper, you will find much more result, also rates, and shows the forward-backward reactions and so on. But here, just pick up this plot because a similar result has been presented by SMASH collaboration, and here, even as you see, the dashed line corresponds to our calculation, but with the SMASH cross sections for this reaction and with their isospin contents. And we are in full agreement with the SMASH in this case. And of course, in the box, we achieve the full, let's say, right thermal equilibrium for these reactions.
So you mean in the box calculation, there are the contribution from potential part is zero?
Contribution of
deuteron, when you count how many deuterons in the system in your calculation, you treat deuteron has two sources. One is from reactions, kinetic reaction like pi NN to pi deuteron, right? And then you add another part from so-called potential part. You just count how many nearby pairs, and the final deuteron you just add the two components, right?
Yes, right. It's for heavy ion collisions, right?
Yeah, but this is some kind of very it seems very very strange to me, because deuteron is just a deuteron. Why it's if you treat deuteron as an independent degree of freedom, then
yes.
The deuteron is what deuteron in your system. You just count deuteron number. So I don't know why you can first count how many deuterons from the kinetic part, and then you add another part from some pairs of nucleons. So because I ask this question because as DEMA and our work has shown that the kinetic equation can describe the deuteron production at the LHC energies and RHIC energies. But in your result, it seems that the deuterons from the reaction, the 3-to-2 reactions is not the dominant one.
Okay, thank you for the question. I can answer the following. In microscopic transport approach, you treat particle as a point-like particle, right? So
no, we don't. We treat deuteron has in our approach, deuteron has a wave function. In DEMA's approach, deuteron is a point particle. Yes.
Yes, that's true. With IMPT approach, yes, you have projections to the wave function of deuterons, which also reduce very strongly the production of deuterons. So in this case, the result is rather similar. But I should
no. Our results agree with DEMA's results because for a large system at LHC and top RHIC energies, the deuteron size is much smaller than the fireball size. Therefore, whether you take the deuteron size into account, it has a small effect.
Here I kind of disagree with this statement. It's the following, because we take also the size of deuteron in coordinate space. And let me firstly come back to comment these box calculations and so on. Here, the deuterons, what comes from potential interactions, they are not treated as a particle. It's treated as a correlation. So we propagate in a code not a deuteron as a particle. You see, we propagate proton and neutron. And we don't store the deuteron as a degrees of freedom from this. We follow space and momentum correlation of this particle during the full history. And we find that due to the potential interaction, this proton and neutron staying together the full history of the collision, let's be a little bit optimistic, the full history of the collision, and they have a negative binding energy. It's really binded object. My binding energy is not -2 MeV, I should say, but it's again outcome of semi-classical treatment. But at least they are bound. They bound by potential interactions. Additionally, here, you have another possibility to find them by reactions, right? And here what we do, we exactly like in the SMASH, we treat them as a point-like particle because in semi-classical BU type of approach or QMD type of approach, you treat particle as a kind of point-like particle, or in this case, particle with some Gaussian widths and so on, but it's with a centroid as a point. So, and in this case, we find, if we do, I should say, if we use cross-section like DEMA and their isospin decomposition, we fully reproduce their result. We would have also a lot of deuterons from kinetic origin. But we think that, as I mentioned kind of here, that we have to take into account the quantum nature of the deuterons, because we cannot propagate in the semi-classical approach the really green function, okay? So, and in this case, we have to mimic the effect with some kind of recipes. And this recipe one related to account the finite size effect in coordinate space, because still these deuterons are traveling together, especially at LHC, with a lot of pions. Try to look in your calculations for the deuteron and look in some radius if there are some particles around. And of course, you will find in the mid-rapidity, we are talking about mid-rapidity, that there are still a couple of particles and some baryons or some mesons, whatever, staying together. And in our opinion, that is not very much realistic that the deuteron as a weakly bound object would survive on this very dense environment. And these excluded volume conditions were introduced precisely to account for that. But it really suppresses a lot the deuteron production. And similar stuff
May I add a comment here?
Space. Sorry?
May I make yeah. So the exclude volume condition, I think it's for baryon, like let's say if you two nucleon, there are baryon inside the two nucleon, then it may not form a deuteron because like let's say because of polyblocking, right? So if the nucleon density is too higher, then the deuteron cannot be bound. But for meson, I'm not so sure because there is no issue of polyblocking if you have mesons inside deuteron. So this
yes. Okay. Well, Pauli blocking is indeed very essential at low energies, and that prevents for deuteron formation for many cases. That's absolutely true. At high energies, at mid rapidity, I don't think that Pauli blocking plays a so important role. Precisely at RHIC energies, we didn't calculate for LHC energies, as I mentioned, just because it's very time costly, and we plan to do that in the future. But at RHIC energies, what we have found that still you have a lot of mesons around. And if you have a mesons in the volume, which is the size of the deuteron, let's say, which is a deuteron has a big elongated wave function, but at least in this even small mean value, which is depicted here. So this meson would also, in our opinion, influence the such small binding energy of nucleon, like of deuteron, sorry, like 2 MeV. And we find that these correlation, which are very sensitive, kind of would not survive if we would have full quantum mechanical treatment. But of course, it's a model assumption. Let me put like that. And you definitely we could calculate without that. Then we would substantially overestimate the data. If we take into account all isospin channel, and that is an important issue, if you take all possible isospin channels, there are much more, by 50% more deuterons you have to produce. If you take
that's not
combination.
That's not the results in our calculation, because for LHC energies, so isospin so what's important is the total dissociation and production rate. So isospin. So if
no. That's I kind of disagree. That's what our study shows, that it's important to write to have this channel decomposition correctly taken. If you put all strengths in one reaction, you can the final answer could be different. And if you take properly all these isospin combinations, because also you have different isospin contents in the matter, and if you really correctly conserve isospin for this reaction, then it leads to, at least at this energy, we found it's this study energy of 7.7 GeV. You see, it's a rather big enhancement of the deuteron production due to the isospin effect.
Okay, maybe we can discuss later, because I have too many questions. So yeah, thank you very much for you.
Thank you. We can discuss maybe later, yes, and some mail exchange.
Sure.
Of course, yes. Okay, thank you.
Thank you very much for your explanations. Thank you.
Thank you. Now I see a hand for Nu. Yeah, please ask.
Yeah, hi, Elena. Thank you for
Hi.
I have a simple question, slide 28. There you compare the potential calculation with with URQMD cascade mode. you say they are in agreement. Is this accidental or how do we understand this?
In a cascade mode, right? You mean in a cascade mode, it's not, I hope it's not accidental. They are not identical, but they're very similar. Because how to say, the Bose model describes the bulk dynamics at this energy rather good, and in this case, if we apply the same cluster recognition algorithms, how to say, we expect that maybe for these clusters should be similar results.
Well, the formation mechanism are different, right? In the URQMD case, they formed after freeze-out.
Sorry, it was a little bit, I was a bit too fast. It was a, sorry, New, let me explain shortly. This was a model study which we did with the coalescence algorithm and MST. We took the Bose model, and for coalescence and for MST, we apply the same routine, even let's say the same physical routine for UQMD and PHQMD. This plot shows what's happened if we apply exactly the same coalescence routine to UQMD and PHQMD. This plot shows what's happened if we apply exactly the same routine, even physically the same routine, to UQMD and PHQMD. And we found that they show rather similar behavior.
But if I understand it correctly, in case of a cascade mode, there's no potential.
Yes.
In case of PHQMD, there's a potential effect, and you emphasize potential is actually important for cluster formation, which I agree. That's why I'm a little bit surprised both approaches are so close to its similar.
Yes, actually, we were also a little bit surprised that with cascade, let's say, with cascade, you are so good. My answer could be the following. It's already rather high energies, right? And it's mid-rapidity data. And if you go to low energies, the influence, as low you go in energies, then it's more influence of potential you would see. Because in this case,
this is accidental, you say, at this energy?
Not exactly, because look, in this case, the particle dynamics are driven to large extent by the collision integral. Even if it's, let's say, string dynamic and everything realized differently, there is a common tendency. We describe a proton spectrum and so on, but of course, in some sense, it's not necessarily has to be like that at all energies if we compare PHSD and PHQMD. And you see, potential line is rather different because it's related to different implementation of potential in UQMD in some non-relativistic way, and very strong repulsive potential what they have, and in PHQMD it's different realization, and you come to different results already.
Thank you. Yeah.
Xiaofeng?
Yeah. Yeah, Professor Ko. Yeah, please.
It's getting too late. I'm just add a comment addressed to what Lu Xi mentioned. I think we know coalescence model works pretty well already at the Bevel-like energy, right, long time ago. And also at the GSI energy long time ago, you do some cascade code follow with coalescence. And deuteron, triton can be reproduced pretty well. Whether you introduce potential or not, doesn't matter that much, right? I think in Nina's approach, all his deuteron, triton come from correlation, therefore she needs potential. But if you do coalescence, then you don't have to worry potential. But coalescence just projected the freeze-out wave functions. Freeze-out proton neutron, they are essentially free. At the freeze-out, the proton neutron essentially has a very weak potential. You just project the wave function into deuteron internal wave function, therefore it works. And that's why the potential probably dominated the evolution if there are many neutron densities are high. But if neutron density is low, the potential is not important anyway. Right? Actually, I think in early days we don't start the
yes.
kinetic approach. We always approach do the coalescence model.
Chimin, can I comment? Of course, let's say I know your work in the coalescence model, and the coalescence model is very successful in description of light clusters. You cannot do that with heavy clusters. And
that I agree. That I agree.
Yes, how to say? My main argument is like that. Coalescence model, it's kind of phenomenological way to see for the correlation of proton, neutron and coordinate momentum state. Your cluster are not bound, right? So they're not bound. You just look for something which is moving together and have a recipe how to identify that this could be the cluster, and you stop any further consideration after freeze out. You say that that's my final cluster and so on. In our case, when I emphasize that it's potential mechanism, maybe you see it's kind of wording. It's maybe not fully true even to call it like that. Of course, it's related to the full dynamics, and dynamics is driven at low energy a lot by potential interaction, but at high energy, as it was related to the question of nu, why it is like that, to this particular plot, is driven by collisions. And what we are doing, actually, potential does not participate in our cluster recognition algorithm. Look, we don't, what we do in reality by calling this potential, we follow dynamics of nucleons, and we are doing photography in a different time. And with this MST method, it's cluster recognition method. It doesn't bind them together. It doesn't look for anything. It's making you statement that these two guys, for example, proton and neutron, or triton, helium, it's working up to very, very heavy cluster, as I have shown. So it's telling you this bunch of nucleons staying together. That's all. And it's telling you they have a negative binding energy. You can compute it. So then you look in the next time, your MST doesn't know anything. You don't propagate cluster by that. You propagate nucleons. What nucleons do? They do interactions, and that low energy potential is important. Maybe you're right, at high energy, to call them potential, we were looking for words. We found word potential, or because they are also collision term is important, and rescattering is important. It's in this case, you are right, but they still follow correlations, because when you compute, I still believe potential is important in this case, because when you compute in molecular dynamics the forces, let's say you take into account two body forces between each potential, each nucleon, whereas in mean field type of approaches, you have a single particle distribution function propagated in mean field. And it's mere correlation. The cluster dissolve faster. When we run the same in PHSD mode, we find a worse result for cluster. Let me put like that.
Yeah, so getting there, I think it's an interesting question to eventually understand why kinetic approach is similar to coalescence approach, similar to your MST approach. They all give similar results. That's very intriguing. Hopefully we can resolve that in the future.
That's answer is might be partially follow, because here, because what we analyze freeze out time of the baryons and where the clusters formed. If you look on the next plot, on the next kind of line, so and freeze out time, the formation of the cluster occurs definitely even before freeze out time, but finalizing interactions definitely happening at freeze out time. It means that the cluster can be formed before, but only those which pass without interaction after freeze out time, they would be survived. And that's, I think, why results are similar.
Mm-hmm. Okay, thank you.
Thank you. I think Jorge wants to say something.
Yeah, thank you. Yeah. Aichelin, please.
Jorge, you're
I think the basic fact what we have here is that we have at mid-rapidity really highly excited state, which is about 100 MeV temperature. So first of all, it's the expansion of the system. And for this reason, it expands with potential and without potential relatively similar, because the potential is small as compared to the kinetic energy. And so for a while, it's basically the same. And then it's just a question how to define a cluster. The clusters are defined in the MST at the time when the contact is lost, and then we are left over with some fragments which are bound. And these fragments we just follow up to the end, and that we call fragment. Now, the coalescence mechanism looks also when basically the interaction stops and then makes by the coalescence radius the same. So also find fragments, they are not necessarily bound, or neurons are not bound. And it seems to be that all is widely dominated by the expansion of a hot system. The details, however, and that one has really to compare then, depends on the action of the potential. I mean, if you look in an order of magnitude size, I think both should give the same thing. If we look now for factors of 2, I think one can really study what is the influence of the potential with respect to the final state which we get by a coalescence model. That would, I agree with Jamin, that is really would be an interesting study. That is also for Nuclei. I mean, that at mid-rapidity we have now this highly excited system is first of all the reason why these clusters disappear, because they are fast. I mean, the relative momentum is large as compared to projectile and target rapidity, where the relative momentum is small, and therefore the clusters just stay longer, even if they are formed finally together and are not recognized by these MST procedures that early.
Well, then it will be nice to see the same exercises at 3 GeV. There we have already lots of data.
At 3 GeV? Yeah, 3 GeV you have.
Yes, I have shown 3 GeV. It was here.
Well, compare with URQMD cascade approach.
But that's Marcus published. I think Marcus, Bleicher, they definitely, I think, publish, and that is our.
I'm looking for the potential effect of the equation of state.
Look, one has to be careful. As one go to energy low, as Elena has shown, the number cluster increases dramatically. There's some kind of 80% in cluster. Then you cannot do the normal coalescence, because normal coalescence by the unitarity, right? You can only do the coalescence as a perturbative approach to light cluster productions. Once the number of light clusters is large, then one cannot treat perturbatively. One has to introduce unitarity.
Well, we already tried with both URQMD and GEM for this light.
Yeah, but not unitarized, but not unitarized coalescence. Unitary coalescence means if I do all the coalescence, I guarantee all the nucleons convert into light cluster. Right? Now we do perturbatively. Right?
Yeah, but I think it would be an interesting exercise nevertheless. I mean, if one just plainly starts with the coalescence procedure and applies this,
that's a way. Let me interrupt. That's a way to introduce unitary coalescence. Actually, we wrote a paper a couple of years ago how to unitarize. You have to into wave packets for the nucleons. In QMD already, you have the wave packets. Much of you wave packet, then the wave projections. That's unitarized. You guarantee the total probability is 1. Each nucleon can convert it to a light nuclei with probability 1 when you add up all the light nuclei, right? So we have to do different kinds of coalescence, right? And that can be done. So we really need to devote a discussion someday in the future. Now I don't know if we can discuss those in 10 or 15 minutes.
Yeah, but you said that the potential becomes more and more important. We see at low energies, at cis energies, that the equation of state influences the fragment yields considerably, which is of course not there in a coalescence model. So for this reason, I think the study in the unitarized model would be really interesting.
No, that's not true, because the equations only affect the dynamics of evolution. But finally, how cluster produced it only depends on the freeze out the proton nucleons, then you do unitary coalescence. Don't remember, original paper about the Pearson. There's no energy violations, right? When deuteron, proton, neutron, they form a deuteron. There's a mean field around, all right? In the high energy collision, you still have a pion around, which will balance the energy, not only the momentum, also the energy. So energy must be conserved just because the binding energy.
But Chiming, I'm sorry.
Approximation.
Yeah.
It's approximation, right?
Yeah, but if you take only a coalescence, then you do not conserve energy. But
it's a 2 MeV, who cares?
Yeah. Well, I mean, it's a small fraction of the
if you
energy,
form a,
but it's a
form a
necessity.
nuclei, of course, it's form a nuclei, then one has to worry. You form an oxygen 16, that's a huge binding energy, right? Then one has to worry. Right.
Yes, but nevertheless, I mean, this fact that the third body is around is a condition that you can form a fragment. Otherwise, you cannot. And to have this freeze out where one make coalescence and third body around is not evident. Besides the collision partner of the
so my idea approach is do the MST during the time evolution of the hadronic matters. As nucleon kinetic freeze out, I turn into kinetic approaches. I don't have to do coalescence. If I do the kinetic approach at kinetic freeze out, I can only reproduce 30% of the deuteron and the triton. I don't get enough, but I need some additional pre-deuteron triton at the kinetic freeze out. That's what I probably can get from MST approach. Okay. Of course, Kireyeu can use kinetic approach, or kinetic approach also face the problem. How can deuteron or triton be bounded at 120 MeV temperature? That's still big questions, right? That we have to wait until Hatsuda can calculate the nucleon potential at a finite temperature. He promised me he will think about it, whether the deuteron can still bound above 100 MeV temperatures.
No, that's absolutely not. I mean, Chiming says this.
Nobody knows. Nobody knows. Nobody knows.
No.
It was a study by Rybke.
It's not true. There's extensive study by the Rostock group and company. And he shows that at moderately light temperatures and moderate densities, the deuteron will not be stable.
No. This is based on the known potential, but we are the pion gas, right? We need to know nucleon potential interaction at the finite temperature. Hatsuda did the lattice calculation of the nucleon in the free space. So I urge him to go to finite temperature to calculate nucleon potential. Is still attractive or not? According to Edward Schurek, nucleon will be more attractive at the finite temperature, finite density. Why? Because chiral symmetry restoration, which make the sigma mass decreases, that leads stronger attraction, right? So according to Schurek, nucleon, all the light nuclei, they are bounded at the finite temperature, finite density, the chiral symmetry restoration, or critical, approaching the critical point. Right.
Yeah,
so
but
that's the unknown questions. Unknown questions where I need to study, and I don't think we can
less a problem
during this short time. Okay.
Chiming, according to Rybke, it's less a problem of the potential. It's a problem of the fact that in a medium you have other nucleons, and these nucleons block a part of the Fermi distribution.
At LHC, nucleon number is tiny.
I think we should have a special seminar on this. I think.
Yes. Yeah, please. I need to
meet something.
Please cut. I need to cut of this.
Sorry.
Yes. That's fine. We have still have a question in the chat. Zebo Tang is asking about the slide 25. Could you go? Yeah, next slide. So he asked why the curves jumps up and down. Yeah, slide 25. 25.
So, okay, sorry, because it's a spline, Susanna made a spline line between real calculation, and of course it's a statistical fluctuation which we obtain because it's rather difficult to get statistics, and microscopic transport calculations, they suffer very much from statistics, as you see, but to have a nice view, she connected by splines. It just, it's just spline connection. No physics in this maximum minima.
I see.
Sorry.
I see. It's purely due to the limited statistics.
Yes, yes. It's just a way to present. She connected by spline, and then she got the figures. It could be steps, might be better than it's fluctuations. Okay, thank you. Yeah, and from STAR we have Python measurement from beam scan, just posted on archive. I think there are a lot of interesting results. Maybe in future you can do that computation. Oh, sure, this will be very, very great, very interesting. Sure, so that definitely we can look at that. Yes. Yeah, that's great. Yeah. Okay, I think we already have a lot of discussion today, and already time is past 30 minutes limit. Okay, I'd like to thank you, Elena, again, and thank you for this very nice presentation, and also the interesting discussion during the presentation. And I think thank you very much. Thank you all for listening for so long, and thank you for very interesting discussion and question. And of course, we are looking forward for your data, because without that, we cannot clarify what's going on. So thank you very much. Have a nice day. Thank you. Bye. 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 Bye.
Thank you. Bye. Bye.
Bye. Bye. Thank you. Thank you very much.